Welcome to this webinar by Oxford Technical Solutions. In this webinar, we will explain why an inertial navigation system is integral to the operation of a mobile mapping vehicle. First though, we need to describe what a mobile mapping vehicle is. Mobile mapping is a method of collecting geospatial information from a moving vehicle, applied to a variety of platforms ranging from cars to trucks, trains to recreational vehicles. Mobile mapping provides a means to efficiently and dynamically map the environment. Mobile mapping vehicles collect data that is used to map features along a route. The data collected using a range of imaging sensors that include digital photographic cameras, video or laser scanners. The features that have been mapped might include slopes or contours along the vehicle's route, the position and type of roadside assets such as signage or noise barriers, the height and structure of surrounding vegetation, or the condition of the road surface itself. The accuracy, precision, and frequency of measurements that are required to map these features will vary dramatically. In terms of data, cameras may be taking multiple images per second, or laser scanners could be collecting 1 million individual data points per second. Regardless of the type of mapping sensor used though, a consistent and known means of georeferencing the collected data is required. If we consider the process of mapping on the move, a mobile mapping system needs to be able to collect data in such a way that users can locate and position features of interest in data collected by the mobile mapping vehicle, all while it is in motion. Positioning these data not only requires knowledge of where the vehicle is located, but also the orientation and onward velocity of the vehicle. Due to the frequency at which data is captured, this is information that needs to be understood continuously throughout the passage of the mobile mapping vehicle. Survey technologies such as global navigation satellite systems are well known and widely used in conventional survey procedures. There are now different constellations of global navigation satellites, such as the US-led GPS constellation, the European GLONASS system, and now also the Chinese Beidou constellation. In this presentation, we will generically be using the terms GNSS and GPS interchangeably when referring to these global navigation satellite systems. However, relying only upon GNSS information will lead to incomplete mobile mapping results. This is where it is important that an inertial navigation system, otherwise known as an INS, is used to deliver a complete mobile mapping solution. So why not just use GNSS data to position mobile mapping vehicles? The use of GPS by surveyors to create and update maps has been commonplace for over 20 years. These systems calculate a position on the Earth's surface by way of timing information received from a network of global navigation satellites that continuously orbit the Earth. To collect data, a GNSS receiver needs a clean line of sight to at least 4 satellites at any one time to obtain longitude, latitude and altitude coordinates. Depending upon the overall distribution of GNSS satellites over a location at any one time, such a clear line of sight might not be possible. Structures in the environment such as tall buildings or overhanging trees can also occlude the receiver from clearly seeing the sky, and can also contribute to outages in the extent to which a GPS can calculate its position. Furthermore, when the GPS signal is re-established, there may be errors in timing that have occurred over the survey that cause the calculated position of the GPS receiver to drift after an outage. This problem can be even more acute when undertaking mobile mapping, as vehicles often travel through GPS-deprived areas where there can be a high proportion of these obstructions, such as in urban centres or forests. Even if the required number of satellites can be seen, the frequency at which location measurements are recorded from a GPS is likely to be different to the frequency at which images are being acquired by the sensors on the vehicle. We therefore need to understand what the location of the vehicle is at times when GPS is unavailable, and can then measure or predict where the vehicle has travelled to in between GPS readings that are received. In addition to accounting for emissions in the GNSS data though, a mobile mapping system must also continuously record the dynamics of its movement along the survey route. For example, how has it travelled between points A and B? Is a vehicle pointing up a slope? Or how fast is it moving towards or past features in the landscape? To do this, we need to characterise the movement of the vehicle in terms of its roll, pitch and yaw, also whether or not it's accelerating or decelerating. Using data collected about this trajectory of movement, we also can calculate the exterior orientation of the sensors on the mobile mapping vehicle. In layman's terms, we need to understand where those sensors are directed towards at any point in time. By analysing this information about the dynamic movement of the vehicle in conjunction with the data collected about its location and speed, we can understand where the data is being collected and is located relative to the vehicle. So, in practice, in addition to the mapping sensors themselves, mobile mapping is best undertaken when a range of sensors are being used to locate the position, direction and orientation of the vehicle, all while it is moving. These additional sensors help fill in the gaps when a location is unknown and usually include GNSS receivers for calculating latitude, longitude and elevation, an odometer for measuring distance travelled, an inertial measurement unit, or IMU, composed of gyroscopes and accelerometers for measuring roll, pitch, heading of the vehicle and the sensors upon it, and a computer processing unit containing various statistical algorithms for predicting the position of the mobile mapping vehicle based upon the accumulated readings from all of the mounted sensors. It is the Inertial Navigation System, otherwise known as the INS, that is a computational system that includes an IMU and takes input from the GNSS and odometer systems where available. And through taking these inputs, calculates the overall most likely position of the vehicle. If there is any omission in the data being collected by any of these sensors used for measuring the position and orientation, then the computational system will calculate an overall best estimate of that position based upon the data being received from the other sensors on the vehicle. In doing so, the position and orientation of the mobile mapping system can be continuously and consistently calculated throughout its mission. What does this mean for our customers? OXTS inertial navigation systems have been implemented to synchronize data collected from a diverse range of sensors on regional level projects for mapping roadside assets. The OXTS integration team has worked with a range of sensor manufacturers to field test mobile mapping system configurations. This ensures a straightforward integration between the OXTS inertial navigation system and the mapping sensor. Here we illustrate the results of working with ZNF to integrate and test the OXTS XNAV 550 INS system with the ZNF Profiler 9012, where after post-processing, the capabilities of the OXTS INS system and workflow enabled overall accuracies of 2 centimeters to be achieved throughout the survey route. Thank you for your attention during this webinar. Should you like to find out more about how OXTS inertial navigation systems such as the XNAV 550 or Survey Plus can optimize your mobile mapping operations, please click on the link below.